In this case, first x coordinate, that is only this 0 and 1. Now over each point I must have a copy of the y axis, and y axis means just a copy of integers. So here now give yourself 2 points and then see how they compare. If they are the same axis, y axis, then you know how they compare. It's just like a copy of integers. So I choose one point here and another point here. Let us say, well, x coordinate is 0, comma, let us say 5, and y coordinate 1, comma 7. Now, what is your interval? Your interval will consist of everything above, but 0, 5 above is meter, and then everything below. But you see, you have a whole list of numbers, infinitely many of them. You see, now your basic open sets are becoming infinite. Very much different from the situation we have here. You see that things, the moment you make a definition, everything is out of control. And everything is dictated already by the definition. You see how things are changing when you just change the order. Okay? So here, open intervals are becoming infinite. You can just write 0, 4, 06 will be there, 07, all these are there, 08, 0 infinity. So only after you exhaust the list with the first coordinate 0, can you go to the next one. But it's an inexhaustible list of infinitely many things. So all those points are in your interval, open interval. So the basic open sets, open intervals are here becoming infinite. Sometimes they can be finite. If they have the same x coordinate, they are finite, otherwise it's infinite. Okay? Alright. So now having illustrated these topological spaces, let us get back to I want to check the time. Another half an hour. Let us get back to some basic notions in topology, motivated from concepts in metric spaces. Okay. So what are the things you study in metric spaces? You study about unit points, closed sets, etc., etc. I am going to just give you basic examples and illustrate them. So, definition. So a set C in X is called closed. Closed if C is, well, if X minus C is open, complement is open, okay? That's it. So closed sets are simply complements of open sets. So another basic notion you study in metric space, the theory is that of limit points. Okay? So a point X, so let A be a subset of X, we say that a point x naught in X is a limit point of A if, so I write a condition here so everybody can see. This is my space X and this is my space A subset, and I take a point here x naught. Okay, if given any open set U containing X naught. So an open set containing X naught is quite often called a neighborhood or open neighborhood. Okay, so open set containing this. So this is my U intersects A at some point other than A itself, other than X naught itself. In other words, contains some point of A. If you don't want to use the word intersect, it contains. Given any open set, U containing this thing, U contains a point of A other than X naught itself. X naught may or may not belong to A, we don't care. If it belongs, throw away X naught from A and look at U intersection A minus X naught. That must be a non-empty set. This should happen for every open set U. No matter how small you choose an open set containing X naught, it should meet A. Okay? Such a thing is what is called a limit point. So in here, in this diagram, you see X naught is right there and it is meeting A at some point other than that. Okay? Is that clear? So, for example, it could so happen that A is, so this could be a situation like this, A, so X, and here you have this A, and you can have a point within X, this could be X naught, and you could have a neighborhood U, okay, but maybe X naught is the only point in there. Even if X naught belongs to A, it could fail to be a midpoint, like if it is an isolated point. Okay? In such a situation, X naught will not be a limit point. Whether a point is a limit point or not does not depend on whether that point X naught belongs to A or not. It's irrelevant. So, try to draw a picture like this so that people will understand. Let A be containing X. The closure of A in X is the smallest closed set. Call it A bar that contains closed set in X, okay, that contains A. So among all the closed sets which contain A, you take the smallest, okay, that's called the closure. So another way of saying the same thing, you see, open sets were closed under arbitrary union. If you take arbitrary union of open sets, that was again open. The closed sets were what? Complements of open sets. Therefore, the collection of closed sets will be closed under arbitrary intersection. So if you give me an arbitrary collection of closed sets and take intersection of all of them, that will again give me a closed set. Okay, so another way, for that reason, another way of saying what is closure of A is just it is an intersection of all the closed sets which contain A. And that will be automatically closed and it will contain A, but it's a smallest closed set. Finished. Okay, so there are many slightly different but equivalent ways of saying the same thing. Now, another thing you study in metric spaces is the notion of dense sets. So let me say that what it is. Okay. So a set A containing X is called dense. Dense in X if A closure is a whole of X. When you take its closure is a whole of X. Notions. Maybe I say a few more things and then we will work out problems in the afternoon because it's not much time. Okay. Yeah, one other thing I want to say is so maybe this is also discussed. It's not really important. Okay. What else do they want to say? Notion of convergence. Suppose that Xn is a sequence of points of X. Okay, Xn is a sequence of points of X. Alright. So in metric space situation, we study notion of convergence. We also study notion of Cauchy, but in the context of topological spaces, the notion of convergence is the most natural one. So I define that. We say that Xn converges to a point A in X if so given any neighborhood, any open set U containing A, there exists an N, capital N, such that Xn belongs to U for all N bigger than or equal to capital N. There in the context of metric spaces, how will you define? Given epsilon positive, there exists an N such that distance between Xn and X log A is less than epsilon for all N small n bigger than capital N. Okay, this is how you will say that. So that is equivalent to saying replacing this U by the open set B A comma epsilon. Ball of with center A and radius epsilon. If you take any ball with center A and radius epsilon, okay, no matter what, how small this epsilon is, all but finitely many elements, terms of the sequence are in there. Okay, so this we don't have notion of open balls. Okay, all we have is notion of open sets. So forget open balls, instead you replace that by open sets. Then you don't need metric. So this is what I mean by saying study of topology is much more general. And not only that, many concepts in which you needed the metric, now there is a way to replace that. Just replace open balls by open sets and it will be fine. Okay? Now, that brings us to this notion of basis for a topology. I will talk about that and these concepts we studied in the morning. Okay? So, but now remaining few minutes, I want to spend talking about these concepts. So, basis for a topology. So this is like just telling you, the definition itself of an open set in a metric space, you will say that is open if it's union of open balls. So the notion of open balls is the most primitive and important one. Okay, so just the same way you can forget about open sets, work with open balls in the metric space situation. Here what you have is, you tell me what are the basic open sets which you should think in terms of open balls. So I give you only some basic open sets. With that as my building blocks, I can generate a topology. This notion came up in Professor Kesavan's lecture this morning. Kesavan was defining for you the measured space generated by a collection of subsets. The sigma algebra generated by a collection of subsets. So some maximums are there, closure under countable union and complementation. You just keep on doing this process, then you end up with a sigma algebra. So just the same way here, what are the closure properties you require? That you keep and you saturate your given collection so that those two conditions are met. What results is here new topology generated by a basis. So what is a basis? Okay, so this is the basic idea. So a collection B, the choice of this alphabet B is to remind you that you are trying to generate open balls. Okay, should have properties of an open ball. Alright, so B, call it a collection B of subsets of X is called a basis. Well, basis for a topology in X, but we just don't bring in the word topology at all here at the moment. Just say basis if, given any two conditions are satisfied. Given any X, in X there is a B in B such that X belongs to B. Number 2, given B1, B2, or let me write here B1 intersection X in B1 intersection B2, given X in B1 intersection B2, okay, there exists a B3 in B. So here, I should write this here B1 and B2 are instant to B such that X is in, I draw picture and then you will see X is in B3 containing B1 intersection B2. Why did we need that? We have here B1, try to draw open balls. This is your B1 and well, it doesn't look like a open ball, but try to draw a picture. Okay. Open ball, B2, and I take a point in here. Now you see the intersection does not look like a ball at all. It will not be a ball. If you do honest balls in R2, the intersection will not be. But you can find a smaller ball, remaining open ball, which contains that and is contained in the intersection. So if this is your B2, then this is your B3, and B3 is contained in this one. B1 intersection B2 contains this given point X, and is entirely contained in the intersection. Okay, so when these two properties hold, you say that E is a basis. Okay, the moment you have a basis, the topology generated by B consists of all sets U which are expressible as a union of members of this is exactly like defining open sets in a metric space. Okay, so B in that context would be collection of open balls, and when is a set U open or open in your metric space, if it can be expressed as a union of open balls. So exactly in the place of open balls you have your collection B. Okay, if that happens, then you say that this is open. So such things you put them in a kit, that is your topology. Okay, so what is a topology? It should be a collection of subsets. Alright, so what type of sets you put in here? If it is to be generated by E, so this is generated by E. Okay, it's like, you know, I just give you some subset of a linear space which spans it. Okay, so the moment that subset is there, if at all these are to be open balls or open sets, then in any topology that will contain B, it will have to have all arbitrary unions of members of B. You put them in your collection and nothing more. That is the topology generated by B. Is that clear? So, the nice thing about it is that you don't have to describe all possible open sets. You just say what are the basic open sets. Okay, like when defining order topology, all we did was just to give you a collection of basic open intervals. Open intervals that form a basis for order topology. Okay, so this concept is very useful. You don't need to bother with carrying a heavy load of all open sets. Enough if you just understand basic open